Hey there everyone, it is Professor Tomney with another Chem Complete video, and we are back at it again. We're going to do some more unknown spectroscopy today, and this is our first viewer submitted question. So on my most recent solving unknown spectroscopy examples, one of the comments said, could you please do the C7H7NO1? And my answer was yes. So I asked Katie to submit the materials to me through email, and that is what we are going to present here. Now I want you guys to realize that when you have a molecular formula, there are usually going to be several structures that it could potentially be. So just stating a given formula is not always going to lead directly to that structure. So you always want to pay attention to what the spectra is actually going to tell you. And as a brief reminder, head over to chemcomplete.com. We have the entire walkthrough guide. It's over 40 pages with solved examples just like the ones you see in this video. It's got additional spectroscopy questions. It really helps you with Mass Spec and fragmentation tables. It's only $5 for the entire guide, and it helps us continue to support the channel and bring you free educational online content like this. So with that being said, let's go ahead and bring up Katie's question, and we're going to solve it together. All right, so here is the material. It starts with the IR up here, and then we have access to a mass spectrum, again with the formula that was put in the comments, C7H7NO. We then have our C13 material, and then we finally have our proton NMR material. So let's get started with solving this. So as you guys know by now, if you've been watching the series and you followed my entire free online course, what we like to usually do when we're starting these is to solve for the degree of unsaturation. So we'll go ahead and we'll do that real quick. If any part of this is confusing at any point, it is important that you go back through the course and you take a look at exactly which part you're confused with. So if we have C7H7NO, we would do the degrees of unsaturation by writing 2 times 7, because it's 2 times the carbon, plus 2. And then we add 1 for the nitrogen, right? So we'll make a note to ourselves, that's for the nitrogen that's present. Oxygens are ignored, and then we subtract 7 because we subtract the number of hydrogens that are present. So that will be the numerator, and then we divide all that by 2 as the denominator. And if you solve this, you're going to get 14 plus 2 is 16, plus 1 is 17, minus 7 is 10. So 10 divided by 2 is going to be equal to 5. Now, general rule of thumb, but not always a guarantee, if you have 5 degrees of unsaturation, you usually have some sort of an aromatic ring. We'll just use benzene as the placeholder right now. Okay, but because we have the ring and the 3 pi bonds, this automatically takes up 4. So remember, degrees of unsaturation are double bonds, triple bonds, and rings. And when you have such a large number of degrees of unsaturation, it's not impossible to have a whole lot of, let's say, carbonyl groups or a bunch of triple bonds strung together or something like that. However, it's usually plausible that you will have some sort of an aromatic ring, and that's very easy to determine with the rest of the spectroscopy as we move along. All right, so we have 5 degrees, and we're going to just table the idea for the moment that we probably have an aromatic ring somewhere in there. So let's move on to the mass spec and just quickly glean what information we can. We have a molar mass of 121. That should be confirmed if we were to add all of the molar mass for each of the individual atoms up for the structure. And then what we want to do is our regular math where we're going to look at the difference between peaks for fragmentation patterns. So we would say 121 minus the first peak we see, which would be 106. And the difference in that is 15. Well, 15 is most commonly a methyl group. Okay? So there are fragments, and this is the mass of a methyl group, 15. Right, there are fragments that are very common that show up again and again with certain numbers. And again, if you get the guide that I have documented all of that in there. There's a table in one of the appendices that gives all the most common fragmentation patterns. It's a very useful reference guide when you're going through this. Right now, 121 minus 78. So in this case, you get 43. Now what's interesting is we also see 43 as a peak pattern over here. All right. So keep in mind, whatever we're subtracting here, this is what was lost, right? So this was lost. And then whatever goes in here was also lost. So that means that it is found by the detector right here as an ion fragment at 43. Okay. And 43 is most commonly a carbonyl with a CH3. So it's an acetyl fragment. Okay, so the CH3, that already makes sense here, and then that's sort of being further confirmed by the fact we have a 43 fragment that's being lost, and that is most likely an acetyl fragment. That is what comes up most commonly there. So this should be easy to confirm because the IR should show us presence of a carbonyl if this is true, and then we'll obviously get confirmation of the methyl as we go down to the NMRs. So if we're looking at this, I briefly want to keep a check on myself. If I have an aromatic ring, do I have room for a carbonyl? Yes, because the aromatic ring would take up 4 degrees of unsaturation, and that carbonyl would be the 5th. But then I cannot have any more double bonds, any triple bonds, or any more rings. All right, so I go up. The IR outside of the fingerprint region to the right here is pretty empty, but it does contain exactly what we need. So at 1690, we see a carbonyl has been confirmed through that very distinct long vibration peak that comes down, right? Now, something that's just interesting to note here, if you go through the course that I offer online, it tells you that the 3000 mark is a dividing point, and it's very important because it tells us if there's anything above 3000 that you have usually some sort of pi bond activity. Anything right below 3000 is simply just your sp3 hybridized carbons. So this little chunk right here that's hanging out is likely the result of hydrogens attached to carbons involved in a carbon-carbon double bond, specifically in an aromatic ring type of fashion. Okay, so that is some minor evidence, but still it helps to confirm the fact that we're likely dealing with an aromatic ring that then probably has an acetyl group on it. So let's take that information and head down to the carbon-13. So now we're starting to get into some more details where we can really start trying to solve the structure and put it together. All right. So first of all, you do have a dept. There are no inverted peaks. So that means that we do not expect any methylene groups or CH2 groups in this example. This down here, because we are below 30, this is probably about like a 25 ppm maybe. When you get something that low on a carbon NMR 13, this is almost assuredly, especially after the mass spec evidence, going to be a methyl group. So you can pretty much write that off. We definitely have the methyl group at this point. Now, what we do want to take a look at is there anything around like the 110 to 150 region? And there is. There's a whole cluster here. And this is confirmation for sure that we have the aromatic at this point. Okay, so again, we always start with suggestions and we continue to scaffold and build on that with more and more evidence until we compile so much overwhelming evidence that we can offer a very, very strong conclusion. All right, so how many peaks do we see here? 1, 2, 3, 4, 5. Okay, now that's interesting because if we consider a benzene ring normally is going to have 6 carbons. And so if I see 5, right, that would potentially suggest that I've got something that is going to be considered an asymmetrical ring, right? Because if I have 5 carbons and there's a total of 6, I really probably should see 6 peaks if there's no symmetry at all. So we'll have to figure out what's going on there in a minute. However, what we can determine is that we certainly have an aromatic set of carbons here, okay? And this one up right there, that small one, disappears when we come up to the dept. So that means that it's a quaternary carbon, and quaternary carbons completely disappear, and that quaternary carbon is most likely going to be the carbon where the acetyl group is attached. So assuming that we've got this group that we've been suggesting, okay, this carbon that's on the ring at that point of attachment, right, and this is an aromatic ring, that would be what's disappearing there, okay, because all of these others would have hydrogens associated with them. And then we can definitely confirm, again, a carbonyl. Carbonyls are also quaternary, so they disappear up in the depth, but especially right around 2, this is probably at 195 ppm. When you get up that high, close to 200, it's almost always a ketone, and that is exactly what we're suggesting, an aromatic ketone right there. All right, so some useful information here. Now, I want you to pause and think about one more factor here. So I'm going to delete a little bit of what I did up here just because I want to make some space, okay, to discuss this. So what I want you to think about is the fact that when we're looking at this, all right, if I'm proposing an aromatic ring, and we said there's probably some sort of issue with this coming up, okay, plus I'm proposing this structure right here, right? And I have evidence, pretty strong evidence for both of these at this point. The question is, how can I justify this? Because this structure, the benzene structure, is going to have 6 carbons. This structure right here is going to have 2 carbons for the acetyl. That's a total of 8 carbons. But if we go back up and we look, we're only entitled to take 7 carbons for this structure. So what am I going to do? If I've got 7 carbons and it's got 8 of them here with the current proposed structure, well, I have to look at cutting one of these carbons out. It wouldn't come from the acetyl group. That wouldn't make sense. But I could cut one of them out from the aromatic group. However, I would have to replace it with another atom instead of carbon. All right. So these are what's known as hetero rings. So for example, maybe you have something like an oxygen that goes into a ring like this and takes the place of one of the carbons. A lot of students have seen this, like cyclical ethers and things like that. Okay, so if we go back up, we have carbons. Hydrogen can't be inside the ring like that as a hetero atom. That wouldn't make sense. So that leaves nitrogen and oxygen. Well, the oxygen's accounted for if we have a carbonyl, and we definitely have a carbonyl because of the IR. So logic would have to dictate then that the only choice is to place a nitrogen in place of one of these carbons. And this makes more sense because now I'm going to have 1, 2, 3, 4, 5 carbons, and that's the number that I counted in the aromatic region. Remember when we said, oh, it should come up with 6? Well, the reason we're getting 5 is that there's probably a nitrogen somewhere in there. We also know for a fact we don't have nitriles because the degrees of unsaturation wouldn't allow for it. And on top of that, we don't see any peaks in the IR for nitriles. Same thing for amines. We don't see any NH2 peaks that are coming down here. So the nitrogen has to find a home at some point, and it's running out of options if we don't place it into the aromatic ring. All right, so hopefully you can kind of logically put that all together and that makes sense. So then we come down to the finale. Let me just move my screen down here a little bit because I want you guys to be able to see the ppm scale. All right, so when we come down here, all right, the integration that I'll write here, it's 3, and then these are each 1. Okay, now if you were wondering how you come up with that, I'm eyeballing this, but because I already know there's a methyl, this has got to be the methyl based on the ppm, around 2.5. That's the only place it could show up. These are all aromatic protons, and on top of that, the relative ratio, if I know that this is a methyl, I look at the height of the integration, and then I look at the height of these. These are about 1/3 the height of this methyl one. So when I compare them, I could safely say if it's 1/3 the height, then it's a 1:3 ratio. So 3 protons associated with my CH3 group, which that definitely is, and then a bunch of 1s down here. All right, and you can see the expansions of them up in these areas. Now, we know that we're proposing the acetyl group, right? So this should be coming together at this point. This next to a carbonyl should show up somewhere probably in the neighborhood of 2 to 2.5, and that's exactly what it does. It also should not have any neighbors if it's attached to the ring as far as hydrogens are concerned. And so when we take a look at this, it should be a singlet, which it is. It's just one signal. We don't have any type of splitting. Then it's completely empty until you get up to the aromatic region, and then we have all of these aromatic signals, right? Now, it could be easy at first to get confused and think that 9 right here, okay, because this is pretty far upfield, I'm sorry, pretty far downfield, that this 9 right here is an aldehyde. However, aldehydes must show up as singlets, and you have a very small split at the top, okay? So what's happening here is the coupling constants, because these are very interesting patterns. You have protons that are basically splitting a signal, and then you have another set of adjacent protons that are splitting the signal again. So when you get into situations like that, you can have things like a doublet of doublets or a triplet of doublets or things of that nature. So to further expand on this idea, okay, I want you to think of it like this. Say that I have the nitrogen here, okay, and this is aromatic structure, right? So as I'm going along with this, I'm going to put this here, okay? I have the acetyl group, and then consider this hydrogen right here. This hydrogen is going to have a hydrogen neighbor over here. It's going to have a hydrogen neighbor over here, okay? So when it sees this group right here magnetically, this hydrogen is next to this acetyl group. When it sees this one, this hydrogen is next to this nitrogen-based portion of the ring. Those are two different type of magnetic signals that it's getting. And so it sees this one and it says, I have one neighbor over here, so I will end up with a doublet split there. And I have one neighbor over here in a different environment, and that will also give me a doublet split. So I'm going to end up with a doublet of doublets. And this particular proton right here, right, would show up furthest away from the electron withdrawing group, so that means it would be the one most upfield, okay, because it's the furthest away from the nitrogen and from the carbonyl group. So that would be this set over here, and sure enough we see a doublet of doublets that are hanging out there. All right, so that's the premise. I don't want you to get too caught up in every single one of these. However, it can become important when you start trying to determine where the rings are going to be substituted in terms of splitting patterns and stuff like that. All right, so this pretty much is the structure that we're trying to propose, and it brings everything to a close here. All right, so we have the acetyl group, that's been confirmed. We have the pyridine structure, all right, and this pyridine structure, we would have a couple of choices as far as where we can put the acetyl group. We could put it in an ortho position, or they would say the 2 position next to the nitrogen, the 3 position, which is this example over here, or the 4 position, which would be right above. Now you have to be careful, because putting it in the 4 position would bring some symmetry to the molecule, and if you put it directly above here and you bring symmetry, that's going to ruin some of the uniqueness in the signals. You're going to start doubling up because you have symmetry, and we said that there was some level of asymmetry to this molecule. All right, so the reason that I would propose that this is in position 3 and not in position 2 is that if it were to be in position 2, meaning right down here or right here, okay, if it was there, these 2 protons would both probably start to cluster together. So this proton here and this proton here. And that's because these 2 protons right here, okay, these would be close to the electron withdrawing groups. So you'd have this one and this one. They'd be further downfield. They'd be at higher ppms. But then these are both away from the electron withdrawing groups. And so what would happen is these would each try to give their own signal, but they're so far away and it's difficult for them to be differentiated that you're going to probably end up seeing some sort of clustering. So you won't get this nice clean separation. You'd probably right around this region right here end up getting just a giant multiplet of that group. All right, so that's not what we see here, and because of that, it's going to be proposed that the structure would be the original one we went with, which would be the position 3, or you can call it the meta position. All right, so I'm going to just draw this up here conclusively so that everybody knows what the final answer is. All right, so based on the evidence that we have seen here, I probably shouldn't have drawn it like that because I need to put the nitrogen in. So based on what we've seen here, we've got this structure, right? And then my statement would be that we're going to keep this guy meta, okay? So that we can get the proper signal ratios that we want here, because we don't really see that clustering with two groups that are two spaces removed and sort of would cluster up together. If that doesn't make sense, you kind of want to get a better understanding of how electronegativity and electron withdrawing groups are going to play with your groups in terms of separating them out and moving them either what's called upfield, that's higher ppm, or downfield, that's I'm sorry, oh my goodness, upfield is lower ppm values, okay, and then downfield is higher ppm values. So this is the final structure that we are proposing here, and this would be the correct structure for this set. So Katie, I hope this helped you. I hope it helped everybody else. And guys, if you have examples out there or you are frustrated, you are welcome to try to get a hold of me, and I can try to do a YouTube video. If you feel you need more individual coaching, you've got a lot of these questions coming up. It's not just this, it's organic chemistry in general. I have very affordable online tutoring prices. We can do it from the comfort of your own dorm room or home. You can check out chemcomplete.com for scheduling, and you can hook up with me there if you're interested in some coaching, and I would be happy to get you through your course. So other than that, if the video was useful, we always look forward to comments and interacting with you guys. And if you hit subscribe, you'll be up to date as always. That's it for now. Take care, and we will see you guys for the next one.